So we just discovered that um, we are using a discriminating loss function or a score function for making our values. And we didn't quite notice that from the graph here, which still looks a little bit weird. We noticed it by looking at the results here and comparing them to what we should have known. Um, we found that it rewarded the majority at the complete expense of the minorities. And if we went even farther on more iterations, that would have just been more extreme. Actually, let's try that. Let's go farther out. So 50 iterations through this, 50 batches through. We got something. Let's try it, just add a 0, 500. Why not? We got some time. Okay, so we've got a bunch. Now this kind of does look a little crazy, but let's look at the outputs here. Looks like it went to the extremes. It said, okay, 0.9 here, like basically 96% likely to be that first one. Now remember, the first two boxes, the red and the orange, or the first two colors for box 0, were almost the same. Like this difference was just a 50 bead box, but this really amplified that distinction. So yeah, really bad loss function. And as we cranked up the number of iterations, we just saw that more extreme. Let's go all the way to 500. And boom, that's like really pushing it out to the extreme. I'm a little disappointed here that we're not seeing not a number. Sometimes if you push these softmax items out to the extreme, actually, if it wasn't a softmax, you'd really see it. Sometimes we get a not a number, and that would have been a good thing to debug too. But we didn't see it here. But still, we just see that clearly something's wrong here. So let's fix our loss function. Um, so uh, let's try out this loss. So here's my usual way of fixing things. Let's not just edit the code. Let's develop something interactively, and then once we've got something we're confident in, we can put it into the code. So our way we're going to do this, what do we want to change? We want to change the score guesses function. So let's see if we can rerun this function here. And I'm going to take out the assignment so we run just the function. And so there is a score. So let's unwrap that function. So we see what did it actually do here? So I'm going to take these two things inside the function. I note that its parameters are guess and beads. So I'm just going to um, rename it so we use my guess, which is the one that we had computed up here. And instead of returning, I'm just going to print, have it change that result here. So here is the place we're going to use we're going to change this loss function. So currently this is just the mean of the probabilities. So you probably have read about the cross entropy loss function. And indeed, from the notes up here, guessing the true proportions for each box is the thing that minimizes the cross entropy loss between the observations and the guesses and expectation. So we should be using the negative log of the probability given to the observed sample as our loss. Negative log of the probability, that's the cross entropy loss. So we already have the probabilities. Now we just need the log of them. So I'm going to delete the mean here for a moment. So we look at the original ones. Now we .log to find the log of them. Notice what .log did. Now I've got a bunch of negative numbers. So let's just look at a few examples. So if we have a tensor of, like, let's say we guessed 0.5. What's the log of that? 0.069. Okay, so whatever bead we got, we had guessed 0.5 on. So really, we should have we should have done better at that. We'd want to push that up to be like a 0.9 probability. So we want 0.9.log. So this is we got a higher value, and it got a less negative number. So negative numbers can be a little bit tricky here, but we've still got something that that is increasing with our score. So our log is a monotonic transformation. So higher numbers still mean higher log outputs. So we could use this, but now we'll have negative scores. Let's let's be okay with that for a moment, but then switch it to loss. So we're going to take these logs and we're going to take their mean. So we take this log here, and now we get this is these are the log probabilities that we gave to each of the observations that we made. Let's take the mean, dot mean of all these, so that we get the sort of average log probability. This corresponds, if you know your stats, to basically the likelihood under a binomial distribution or a multinomial distribution if we had made each one of these guesses. Uh, so this is a mean, or basically a sum of log probabilities, which is corresponding to a product of original probabilities, and that is if these are independent observations, that is the joint probability of all the observations together. So this not just it isn't just mathematically or convenient in code to take the mean of all these things. It actually makes mathematical sense. So we're going to take the mean of these, and now we get a negative 0.2 as a score. So positive, this going up is better, so it's a score. We might want to switch this to loss later, but let's leave it at score for now. So all that meant was, what did we do? We took the dot log, and then we took the mean. So let's just try this. So if instead we use this loss, what happens? Well, our plot is still kind of crazy. We'll see why in a moment. But look at these proportions. 0.46, 0.33, 0.29. That's starting to look more like what we had. Boxes, sum, axis 1, keep them true. 0.4, 0.36, 0.23. That's getting closer. And this one, that's also getting closer. So something's looking pretty good. We're still, we've got this negative thing here. Maybe we don't want that, but something starting to look right about this output. But what about these updates here? Something looks kind of crazy on that. So tune back in. We've made the major change that we need to do now. This converges to the right thing. We just need to see what's going on and just kind of tweak it up a little bit, but we're really almost there. Tune back in for the next video.